If you're an animal and you're not at the very top of the food chain, your life basically boils down to one single, all-consuming problem. How do you avoid getting eaten? So today, we're going to dive into one of evolution's most popular answers to that question: just living in a group.
I mean, just look at this gecko. Imagine you're him. You're all alone. You're exposed. Every single shadow, every little gust of wind could be a predator. When you're a solitary animal, the pressure is just relentless, and the margin for error is razor thin. It is a life of constant, non-stop vigilance.
So this is it, right? This is the ultimate question that natural selection is trying to solve, over and over and over again. When you're on the menu, what is the best possible strategy you can have to make sure you see another day?
And more often than not, the answer is this. Don't be alone. Get a crowd. Surround yourself with others of your kind. Because, as we're about to find out, there is some serious safety in numbers. But how exactly does that work?
Okay, so let's really break down the mechanics here. There are two main reasons, two primary mechanisms that make living in a group such a powerful anti-predator strategy. And getting a handle on these two pretty elegant concepts is really key to understanding a central debate in behavioral ecology.
So first up is an idea that's so simple, it's almost deceptive. It has absolutely nothing to do with fighting back or hiding better. It's just pure, unadulterated probability. It's called the dilution effect.
This is where thinkers like W.D. Hamilton propose that maybe individuals group together for a pretty selfish reason, basically as a form of cover seeking. The logic is, I'm going to join this group, and I'm just hoping the predator eats someone else instead of me. Your personal risk gets diluted across the entire group.
And the math, well, it really is this straightforward. Think about it. If a predator is going to make one attack and you're all by yourself, your risk is 100%. But if you're in a group of 100, your individual risk just plummets to 1%. That is a massive safety benefit just by showing up.
Now, what's really cool about this slide is how perfectly the theory matches up with reality. This is a classic study that looked at fish attacking water skaters. So on the y-axis, you've got the attacks per individual, and on the x-axis, you have the group size. And look, as the group gets bigger, the individual risk drops exactly like the math of pure dilution predicts it should. The real-world data almost perfectly traces the predicted line. It's beautiful.
Okay, but wait a minute. You might be thinking, don't bigger groups just attract more predators? And yeah, that's a fair point. But this study on wild horses and inviting flies shows that even when that's true, dilution still wins. A large group of 36 horses did attract more flies in total, 108 versus only 30 for a small group. But here's the crucial part. Look at the attacks per horse. It dropped from 10 down to just 3. The dilution effect still provided a huge net benefit. All right, let's switch gears and move to our second mechanism. This one is less about math and more about, well, psychology. This isn't about reducing your odds of being chosen. This is about making it hard for the predator to choose anyone at all. This is the confusion effect. Just imagine a swirling mass of bodies, or fins, or wings. It creates a total sensory overload. For the predator, trying to lock onto a single target becomes this massive cognitive challenge because other individuals are just constantly crossing its line of sight. You know, there's a great analogy for this from the source material that makes it instantly clear. If I throw one ball at you, it's pretty easy to track it and catch it. But what if I throw 20 balls at you all at once? Suddenly, it's much harder to focus on and catch any single one of them. Same idea. And this graph just nails the point home with data. What we have here are 4 different aquatic predators. And for every single one of them, squid, cuttlefish, pike, perch, as the prey's school size got bigger, their capture success just dropped off a cliff. The mere presence of the group was actively making them worse hunters. Of course, evolution is an arms race, right? So predators have developed a counter tactic. To get around this confusion effect, they often target any individual that looks or acts different from the rest, the odd one out. This oddity effect is a key piece of the puzzle, and it's a big reason why conformity can be such a powerful tool for survival. So, up to this point, grouping sounds like a perfect solution, doesn't it? But in evolution, there are always trade-offs. The benefits of living in a group don't come for free. They come with a very distinct set of costs. And this table really lays out the fundamental dilemma. All the benefits we've talked about, dilution, confusion, they're on one side of the scale, but they're weighed against some pretty significant costs on the other side. A big group is way more visible, you've got more competition for food, and disease can spread like wildfire.
Every social species out there is constantly doing this evolutionary cost-benefit analysis.
Which brings us to the real heart of the academic debate. We've got these two powerful mechanisms, dilution and confusion, and both are clearly supported by a lot of evidence. So the big question for researchers isn't if they work, but under what circumstances each one becomes the more important, the more dominant protective force.
And the answer, as it so often is in ecology, is it depends. The importance of dilution versus confusion can totally shift based on a whole bunch of factors. Is the predator an ambush hunter where maybe dilution is more critical? Or is it a pursuit predator that can be completely thrown off by confusion? Does the prey move in a coordinated school or more of a chaotic swarm? The specific context of the interaction, well, it's everything. So to make this a little more real, let's take a look at the agile Antechinus. It's a small marsupial from these forested areas of southeastern Australia. This little animal relies on these very strategies for its survival, but it's facing an environment that's under increasing pressure from things like severe drought. And this brings us to our final and maybe most critical question. We've seen how elegant and effective these evolutionary strategies are, but they evolved over thousands, even millions of years in relatively stable conditions. As climate change increases the frequency of extreme events, like drought, which can dramatically alter population sizes, resource availability, can these ancient behavioral rules of the safety dance adapt quickly enough to keep pace